Yeah.
Okay.
Recording in progress.
Right, good morning. So good morning to those of you on Zoom and those who have turned up in person. And I'm grateful that those of you who endured 2 lectures last week are coming back for a third. Shows up. I'm very grateful. Right, so I'll remind you where we are, just our roadmap. Last week we had an introduction to the experimental techniques. Where is a good place to do flavor physics? I'm stressing here the hadron environment, and in particular the LHCb experiment. We had a discussion on CP violation measurements and constraining the unitarity triangle. Today we're going to focus on flavor changing neutral currents. These are decays which are highly suppressed in the standard model, but in where we might expect new physics to manifest itself through enhancements or perturbations to kinematical distributions. So this is today's task, but I just want to go back to one hanging point from the lecture on Wednesday last week. We talked about flavor tagging. I explained that if you're wanting to make a time-dependent CP violation measurement, it's necessary to know whether your neutral meson started as a B0 or a B0 bar. Okay, and to do that, we flavor tag. And for those of you on CMS, I want to be very clear that flavor tagging has a different meaning in flavor physics. In flavor physics, what we mean by flavor tagging is distinguishing whether the event started as a B0 or a B0 bar, not just whether the jet had a B in it or a C in it, which is the terminology which is used more often in high PT experiments. Okay, so flavor tagging is important and it's necessary for CP violation measurements. But I mentioned that flavor tagging is actually intrinsically better in the E plus E minus experiment if you're operating at the epsilon 4s than if you're operating at the LHC, or indeed if you're operating at the Z0. And I left this as some floating piece of homework to try and stimulate you and ask you to contemplate why this might be so. So I guess I should try and answer that question. I don't know if any of you did ponder it. I won't pick out anyone in the audience and ask you. But I've just written two slides here to try and make the point. Okay, so to recapitulate, to determine whether the meson of interest was a B0 or a B0 bar at birth, in the simplest case, in fact, there are other ways we can do it, but in the simplest case, what we do is we look at the other B hadron in the event. And on this slide here, I'm considering the case where we are at the LHC. So at production, we have a B0, so that has a B bar quark in it. So that's the meson which decays into the J side K short eigenstate. That's the meson with which we do the physics. But what we can do, we can look at the other meson, and this other meson will have a B quark in it, and let's say it's a B minus, and then we can hope that that might decay semi-leptonically. And if it does to a muon as here, the charge of that muon tells you the charge of this B, and therefore it tells you what the charge of that B was at birth. So by looking at the charge of this muon, we can infer the flavor of the meson we're interested in. That's flavor tagging. Now, of course, it may not decay semi-leptonically, but there's other things you can use. For example, it can this charm quark here will then decay into a strange quark, and that charge, or the charge of the kaon involved, if it's a charge kaon, will also carry a charge correlation. So there's other techniques we can use, but this is the simplest one. Okay, so I've said that the other B meson here is a B minus, but at the LHC, because there's many particles produced in the collision, as the B's move apart, there's a huge amount of energy. As they hadronize, you have the possibility not only that it's a B minus, but it could be any one of these here. So I've given and indeed there's other possibilities as well. So I've written down a whole bunch of possibilities, each of which has a B quark in them. Okay. Now, this method works in all cases. All of these can decay semi-electronically, so that's fine. But let me just point out that in these two cases, you have a neutral B meson, and these can oscillate, right? So they can change from a B to a B bar to a B to a B bar. And if that happens, then you rapidly lose the correlation with the other B in the event. Because as soon as it oscillates, this B quark becomes a B bar quark, and then the charge correlation becomes diluted. And in the case of a BS meson, this oscillation is very, very rapid, so you essentially lose all information. So this issue means that at the LHC, this flavor tagging, statistically it still works, but it suffers a dilution from this effect. Okay, now let's go to the upsilon 4s. So life is different here. So this is the E plus E minus environment. This is the environment of Bar, and Bell, and it's the environment of Bell 2. And there are no fragmentation particles. You just produce a B and a B bar. Thus, if you've produced a B0 meson, this is the one we're interested in, which decays to J psi K short, you know that the other meson is a B0 bar. So the situation is intrinsically simpler, but you then might say, aha, but that's B0 bar, that's bad, because you've just explained that the other meson in the event can oscillate, or mix, we use these two words interchangeably. And if that happens, then you will get this loss of information, because this B bar quark will change to a B quark, to a B bar quark, etc., etc. However, in this case, this does not happen. Mixing does not occur until one of these mesons decays. Okay, and this is a beautiful, beautiful feature of the upsilon 4s. So why is this so? So let me try and explain this, and I hope I've done it correctly. So the upsilon 4s is a spin 1 meson, and it decays into two Bs, which are spin 0 mesons. Therefore, to conserve angular momentum, these must be in an L equals 1 state. Okay. Now, because there are no fragmentation particles produced, you just have these two mesons. These therefore exist. These two mesons alone exist in a coherent wave function. Let us hypothesize that one of the mesons does in fact mix. So let us hypothesize that this B bar becomes a B through oscillations. If that's the case, you would then end up with two identical B mesons. A B meson is a boson, and Bose-Einstein statistics requires that the wave function is symmetric. Okay, so can this be satisfied in this case? Well, we've already decided that the orbital angular momentum state must be L equals 1, and that is anti-symmetric. So in this case, you would have a situation where you would have two identical bosons in an anti-symmetric wave function, and that can't happen. So this means that mixing or oscillation does not occur until one of the B's decays. So they can fly millimeters, even centimeters apart, but until one of them decays, no oscillations occur. And for this reason, this dilution effect which exists at the LHC does not exist here. Hi.
it as like the both the B and B bar are oscillating, but in a sync manner, such that whenever B bar goes to B, the entangled B0 goes to B bar.
Interesting point. I hadn't thought of that. I suspect the answer is yes, you can, because I imagine it has no observational difference.
Yeah. So, yeah. Okay.
So yeah. I mean, I don't want to. I mean, I don't want to push too deep into the mysteries of quantum mechanics here. All I know is that this very much happens. It's one of the most vivid demonstrations of, if you like, the EPR paradox I know.
I mean, what I understand from the question, if the B0 mixing to B0 bar and the vice versa, if that is happening exactly at the same time scale, that is one and the same, right?
Yes,
whether they mix or they don't mix.
It's
right?
not observationally, you couldn't tell them apart. So I think it's, yeah, it might happen, it might not, with the, since there's no observational difference.
Right. And just one point I think all of you know, but I thought this L equal to 1 being antisymmetric, that comes from YLM, right? The spherical harmonics, and the parity is -1 to the power L. Just to, I mean, you all know that, but I thought I will remind you.
Okay, so having cleared this up, I want to move to today's lecture, which is a little shorter than yesterday. So this is, we'll be talking about flavor changing neutral currents. There's a huge number of these. I'm going to focus on really just two examples. And then at the end of the lecture, I'm going to talk about something which is definitely not a flavor changing neutral current, but I think sits best in this lecture. Okay, so these are FCNC decays, the ones which proceed through higher order diagrams. They're suppressed in the standard model. And in the standard model, you can, I mean, it's just an assertion, you cannot have a tree level flavor changing neutral current. You need a higher order diagram. Therefore, they're suppressed, and therefore they are susceptible to new physics contributions. So a famous example, the canonical example, is the penguin diagram. So here you have a B changing to an S, or much less likely a D, through this loop here, where the dominant virtual particle is the top quark, and you radiate a photon. This is a radiative penguin. You can also have a gluonic penguin. Here's one being drawn by John Ellis, and he indeed is responsible for the name, allegedly because he lost a bet playing darts that he would introduce the word penguin into his next paper. Indeed, you have to do some gymnastics to make these diagrams look like a penguin, but John has managed it here. So it was already realized that these processes are very interesting ways to probe what's happening in the standard model. Are these processes actually there? Do they happen at the rate you expect? And indeed, this was first observed by the Clio experiment in upstate New York in 1993. So there, the decay B to K star gamma was observed at a branching ratio of 10 to the -5. Okay, so the interest, of course, to remind you, is that in these diagrams, in these loops, you may not just have the top quark, but you may have other new physics particles contributing, and potentially very heavy ones. And they could change this branching ratio. Okay, so I won't say much more about B to S gamma. It's something that you can study very, very well at E plus E minus machines. But you can also do it at the LHC. So just to be clear, this is this is an example of a B baryon decaying into so this is a lambda B into a lambda and a gamma. So it's the same underlying Feynman diagram as I just showed you. Here you see a clean peak here above some background. So this is already quite surprising. At some point, nobody imagined that you could do this at hadronic machines, but you can. And what's more, once you've seen this, you can do more than just measure the branching ratio. For example, you can go and measure the photon polarization. In the standard model, the photon is expected to be almost completely left-handed. How do you get a handle on the photon polarization? Well, what you can do is you can you can look at well, this angle here, for example, which is the angle between the momentum of the what is this? It's the proton which comes from the lambda decay and the lambda b momentum, or the negative of that in the lambda rest frame. The point is the lambda decays, and the distribution of these final state particles carries information on the polarization of the photon. And you can measure this, and you find that indeed it does seem to be within the current statistics left-handed, which is a standard model-like. But I don't want to dwell on this. I want to pick up for more discussion what I call the golden FCNC mode, which is BS to mu mu, and indeed B0 to mu mu. So like as discussed, these can only proceed through suppressed loop diagrams. There are several you can draw. I've just drawn one of the simplest examples here. And if you look at this, you see this is suppressed in all sorts of ways. There is, yes, VCAS, the slides have been provided. Gagan should just upload them somewhere. I'm sure he will do that. Yes. So the answer is yes. So this process, if one, this process is suppressed through the fact that you need these higher order loops. It's suppressed through CKM elements. It's also helicity suppressed. If you remember, if you think about why the pi0 decays more often to the muon and a neutrino than to an electron and a neutrino, that's helicity suppression. Helicity is also suppressing this. So pretty much every rule in the particle physics law book is being deployed on this BS meson and saying you cannot decay in this manner. It's not completely forbidden, so it happens, but it happens very, very rarely. In the standard model, it happens at a rate of 4 times 10 to the minus 9. So 4 in a billion. So this is incredibly rare. B0 decays even more rarely than this. So this is very important thing to look for, because again, if there's anything non-standard model, for instance, a SUSY particle, you can imagine that this would perturb the branching ratio and enhance it. So people have been looking for this for a long time, particularly those interested in SUSY. This decay has high sensitivity to SUSY models with high tan beta. And the search had been pursued for over 25 years. So in the last days of the Tevatron, there were rumors of sightings there. Indeed, CDF claimed something, but that went away. But it eventually was found. Well, let me, before telling you how it was found, when it was found, let's explain how it is found. So the issue is that there's lots of B decays that look rather similar to this. Okay, so but usually with missing particles. But rather similar is very dangerous if you're looking for something so very, very rare. So analyses were developed which were not cut-based, but involved machine learning, boosted decision trees. So this was the early days of the LHC, and these were really, I think, the pioneering analyses for employing such techniques. This was done both by LHCb, and CMS was also a leading experiment in this search. Just to give an example of one variable you can look for, your BS to mu mu, well, your BS will be produced at the interaction point, fly some distance, and then decay into 2 muons. So if you can reconstruct these 2 vertices, you have a vector in space. You have another vector coming from the momentum of the 2 muons added together. So if this is a true decay, you would expect these to momentum vectors to be parallel. But if there's missing energy, if this decay had something else involved, in general, that would not be the case. So that's just one signature used. And there's many others. So you could construct a BDT, the output of which for the signal should be flat, and it should be falling for background. Okay, so after, surprisingly soon, I mean, the Higgs turned up rather soon in the early days of the LHC. BS to mu mu did as well, and this was surprising, and this was certainly the at that time the holy grail of flavor physics. So here you see the result from a combined analysis of CMS and LHCb. This combined analysis yielded a 5 sigma observation. So here you see the mass spectrum, the invariant mass of mu plus mu minus, and this is for you can look at this in various bins of BDT output. So if you're at this end, then your event should be very signal-like. If you're at this end, it should be background-like, or dominated by background. So this is, I think, an example of the mass spectrum in the more signal, pure region of the selection. And you see indeed that there's definitely a peak there, and this is the branching ratio. If you measure this, came out at something like 3 × 10⁻⁹, though with a significant error. So this is definitely an observation, and interestingly, it is compatible within those rather large uncertainties with the standard model expectation. Now, very intriguingly, on the left-hand side, there seems to be something going on there. And I remind you, there's this other decay, B0 to mu mu, which would be on the left-hand side because it has lower invariant mass. And that is supposed to be suppressed by a factor of 30. But in this early analysis, this seems to be there at a higher level, but it's not very significant. And indeed, if you plot BS to mu mu against B0 to mu mu, the branching fractions, here's the standard model. And you see that, well, the result is compatible with the standard model, but there's this hint of a larger B0 to mu mu branching fraction. So this was the first observation. Since then, I mean, having observed something, you want to measure things as well as you can. Here, it's very important to measure things as well as you can, because the actual theoretical prediction is actually very, very clean indeed. And this is the current state of play. So this is analyzing essentially all of the run 1 and run 2 data, though not quite in Atlas's case. And here you see these peaks are now very, very clear indeed, certainly for LHCb and CMS. Here are the current values of the measured branching fractions. In fact, CMS has the most precise result. This is a channel which is very suited to CMS because it decays into 2 muons, which is easy to trigger on. And you will see that the precision is something like 10%.
Sorry, since we're talking of a comparison between CMS and LSCB, and just what you just said, so the one point obviously where LSCB profits is the hadron identification. So getting a better control on the peaking background.
Yes.
But what you are saying, the dimuon mass resolution as well as the triggering advantage for CMS. So that's kind of wins over, they win over the hadron identification part if I want to make a comparative thing. Is that fair to say that?
Right. So, okay. So the first thing you say, these results are really rather similar. But yes, there's a peaking background. You can have decays such as B to K pi, where both of the kaons and the pions are misidentified as muons. Okay, so this is a peaking back. This would come right underneath the signal. You might say, well, you're very unlucky to misidentify 2 hadrons as muons. Well, yes, you are, but you're looking at something with a branching ratio of 10⁻⁹. So this is contributing here underneath CMS. So what really matters here is that you just have good muon identification, okay?
Not just any.
Yeah, no, you don't trigger on a single muon. Yeah, you require that there are two muons within a certain mass. Okay. So that this so what really matters here is your understanding of the muon misidentification. What is maybe interesting is, well, earlier we saw some hint of the B0 to mu mu. So do we see it here? Well, the experiments have different sensitivities because here, to tell these two decays apart, you need good invariant mass resolution. First thing to say is that Atlas has very poor invariant mass resolution. So if this decay was there, the B0 to mu mu decay, it would just be sitting under here. You would not be able to distinguish it from BS to mu mu. CMS is somewhat better, and it will improve still with the phase 2 upgrade. LHCb has the best invariant mass resolution, so you can see a separation. So there seems to be something going on here, maybe, but it's not significant. Okay. So at the moment, all we can say is that we have seen. Well, let me go to the. You'd like to see all these results combined, but yeah, and actually combining results is actually not very difficult to do. But the people on experiments and collaboration, they make a big song and dance about it, and it takes for years, and it never happens. The same is true of W mass combinations. So what you see here again is just plotted from each experiment on the horizontal axis, the result for BS to mu mu branching fraction. And you'll see in each case it's quite close to the standard model. And so, but on the vertical axis, that's the B0 to mu mu. So at the moment, we have rather low sensitivity to this. Okay, so actually seeing this decay is a massive achievement of the LHC era, and it's already actually seeing this has actually excluded many new physics models. But what you want to do is to go further, right? Hi.
Okay. Two questions. There is no mention of Atlas. What capability is Atlas now?
It's there. It's there, Atlas. Well, you can see it. They have not analyzed all of their run 2 data. Atlas is for this analysis is the poor relation because it has rather poor mass resolution. So it will never compete with Atlas or with LHCb or CMS.
One aspect of Atlas tracking is somehow not able to exist as well as CMS.
It's just a magnetic field for.
So it's a 3.8 Tesla solenoidal magnet. Vis-a-vis that you have this 2 kind of magnet, no? That you have a toroidal as well as the. So none of them really can compete with 3.8 Tesla. So it's unless you change the magnet.
Yeah. As I said, the CMS, the resolution here will, I believe, improve, not because the magnet's being changed, but the upgrade to the tracker for your phase 2 upgrade will give improved performance.
Small, statistically.
Yes.
Is there any possibility that it's a mirror of the main signal, but some fraction of the tracks are somehow sampling a slightly different magnetic field?
No, so the question for people who won't have heard it on Zoom, I've been asked about the light green on the LHCb plot, asking whether is this a feature of tracks passing through a different region of the magnet and having a different resolution or some such thing. No, we understand our magneton tracking very well. So of course the main signal has tails, and these are studied on control channels and they are modelled, but this is sitting on the B0 mass. I mean, what I don't want to make a big thing of this at the moment, because at the moment there's no evidence that there's anything there. It's just that we have the resolution. If there's something there, we would see it. So it's part of the fit, right? So you can see the green there, but in the data there's not. It's not a significant signal.
So.
Yeah, no, we are very confident that we have sensitivity to something sitting there. Yeah.
You made the statement that if it's part of the fit, and that if it was there, you'd. So are you fitting for a bump at each, or a bump that is somewhere in the mass range?
No. We're not just fitting for a bump anywhere. This isn't like a new particle search. We know what the mass of the B sub S and the B0 is, and we know what the mass of each of these components are. Having said that, they may actually probably still a free parameter in the fit where the bump is.
And your statement that there's currently no evidence is that statistically those parameters are consistent with that bump not being there. Or...
At the moment, yes. Okay. We see that. Okay, this is two-dimensional space, so okay. In the standard model, it would not. I don't know what the significance is, but it's 1 or 2 sigma. Okay. Yeah. It's less than 3 sigma. Yes. Yeah. It's not. Yeah. It's not as there it looked. This was the very early analysis. This looked potentially interesting, but the error bars were big. But you see, it's shrunk down.
In this plot, so the previous plot. So the previous slide. Sorry.
This one or
yeah, this one. So looking just at the data points, I do not really see 2 peaks. I mean, so yeah. So why are we deliberately trying to fit
2 peaks? Well, again, this was. Okay. I put that there for historical reasons. So this is what the data looks like now, all right? But again, you know what the mass of the B0 is, and you know what the mass of the B sub S is. So you can make a fit model, which where you're asking for, you're saying find me a peak at this mass. So sure, yeah. If the model was completely unconstrained here, it would, the best way to fit these data points on its own would just be with 1 broad peak. I agree, but that would be stupid because.
So on the previous slide, you made the comment that combining from multiple experiments should be trivial, but people take a long time doing it. But isn't this the sort of thing that makes it non-trivial?
Yeah. I was being flippant.
Okay.
You need to you need to do it carefully. It's not trivial. Though your first order guess would be not far off reality. What I would like to, what frustrates me is that people who get the job of making these combinations, and it's the same for B sub S, it's the same for the Higgs, it's the same for the W mass. they then they really like these jobs, and they consider themselves high priests, and they say, oh, you can't rush us, and they go and they have meetings, and they take 1 year, 2 years, 3 years. It's a non-trivial job, but it's not a 3-year job. Yeah. So yeah. So.
Yeah, I agree.
So when Atlas have finished analysed all their data, I think there will be a combination which will come out of the full run 1, run 2 LHC. Okay, but if I may just draw a line under this part of the discussion, what I'm saying, so it came in where the standard model says it should, but this is not a, okay, it would have been great if it hadn't, but the fact that it's done this has been very positive information, because it's excluded certain classes of new physics models. This is, for instance, the 95% confidence level exclusion region in for a charged SUSY Higgs against tan beta. So in this horrible yellow, all this region is excluded just because of the observation of beta mu mu. What have we got? Sorry, this gentleman's. What did you wish to do? I didn't. People outside, there's people adjusting the Zoom window here. I'm not quite sure why. You want to hide that thing at the top? You want to hide this? Oh, right, I understand. Oh, right. Sorry, yes, yeah, I now see your problem. It's excluding my text. Okay, right. So yeah, this observation has excluded a swathe of supersymmetry space, but I'll remind you that the theory prediction is very clean, so we want to actually you want to keep measuring until you reach that theory prediction at least. And also certainly see this other decay, so some new physics could enhance zero mu while doing it for the S mu mu. And indeed the ratio of branch fraction of the S mu zero mu, that's a pretty observable. That's super clean. So you want to observe both these and measure the ratio of these branch fractions as well as you can. So this is the next step in your journey.
How this charge is related to that kind of chemo, so that it is constant of the mass and the antenna versus charge.
Because you've done some of the diagrams you draw, it's not the diagram I had here is a good example. But some of the standard multiple processes like W is in, which you can replace with charge pegs. So there's a real contributing high diagrams, and you can some of them you can naturally put a charge things in there. Okay. I think I want to accelerate to the next main topic. Maybe the point I just want to make is that one thing clear is that initially you thought it would be impossible to see this rare decay. Now we've not only seen it, but the actual samples of decays that we reconstruct, you can do things like measure the lifetime distribution of these decays, and see that down here by all experiments. And this is a fit with lifetime of decay, which again has potential sensitive to new physics in a way that quantum fraction itself doesn't have. And these CP violation measurements I discussed last week, talk about PXW, that's a CPI stage. You can imagine actually measuring pH this decay when you have enough sample large enough. So this is an incredible prospect. Okay. But the second topic I want to talk about is a decay which is not rare, but it has many of the same features, and I've drawn some diagrams here. But this is the process LL. LL indicates a lepton. Initially, I'll be talking about charged leptons and usually about muons. But in the end, we'll also open the possibility that you could have a neutrino. So this is an incredibly rich system. The poster child here is V0 to K star LL. Why is that particularly of interest? Well, the K star decays into two particles, and you have then various angles you can measure in the final state, and therefore you can construct a whole bunch of kinematic variables, and I'll show you those in a moment, which depend on these angles, and you can measure them as a function of the invariant mass of the two leptons produced. So you can measure this double differential cross-section, and this gives you enhanced sensitivity to anything that might be happening here. You have very strong sensitivity to the helicity structure of any possible new physics. So this has been, so here indeed is a double differential cross-section. We'll look at this in detail, but again, this is with respect to Q squared. This is the invariant mass of the dilepton system. And on many of the plots I'll show you, there'll be an x-axis, which is just that. And this depends on these angles in the decay. Also involved is the fraction of the longitudinal polarization of the K star, and this AFB. This is the forward-backward asymmetry of the dilepton pair in the B meson rest frame. But there's also all these coefficients in front here. So in principle, you can measure these coefficients and you can compare them with what the standard model says they should be. So people have had a lot of fun doing this. Let's this is a busy slide. I just want to make 2 points. One is that rather than deal with these coefficients here, people often deal with what are called optimized observables, which are constructed in this manner. It's hard to visualize what these mean, but the reason these are constructed is that these are much less sensitive to form factor uncertainties. So the problem of this decay is you've got a hadron in a final state, so there's gluons running around. So QCD uncertainties become an issue, and you can minimize those by dealing with these sorts of observables. And these have the nomenclature is very boring, I'm afraid. You're going to hear a lot about P5 prime. It's excited a lot of interest, but that's the most tedious label you could give something which has excited the number of papers that it has. Okay, so just to give you the idea of the impact of the LHC, people already at the time of the B factories knew that these decays were good, and they were able to reconstruct a reasonable sample, like 250. And what they tried to do was to measure this forward-backward asymmetry. So again, this is something measured as a function of Q squared, the invariant mass of the dileptons. And this forward-backward asymmetry in a standard model is expected to start at 0, go low, pass through 0 again, and go up. The reason you see nothing here and here, that's where the invariant mass of the two leptons equals the J psi or the psi prime. And there the physics is very, very different, and it's long-range physics. So this we leave out. These are really control regions, but they don't tell us anything interesting with respect to new physics. So what was intriguing, this very early B factory measurement, is that it seemed that the data was somewhat higher than the standard model prediction, and this gave people a lot of excitement that something was happening here. That was just with 250 events. But with the LHC, you get this just statistical muscle. And here you see, here you have from LHCb almost 5,000 candidates. And you see, if you look at the points, they are broadly following the standard model prediction. So this high behavior here is not borne out with more statistics. However, if you compare the points with the detailed predictions of the standard model, with some uncertainties, because these predictions carry their own uncertainties, you see that there does seem to be something odd going on here. This point is low, this point's low, this point is low. Again, this region and this region is excluded because that's where the J psi and the psi 2s are. And the physics there is very different. So what about these optimal observables? So these really tedious things called like here. So I'll just show you one, which is this so-called P5 prime. So this was looked at with earlier run 1 data, then looked at again with run 2 data. We haven't looked at it with all of the run 2 data. In the standard model, you expect this sort of behavior. These boxes have not continued here because this group has not made predictions in this region. Okay, you can take off the shelf predictions from a whole, many people. They are either more or less conservative with their uncertainties. I said this observable is constructed to be as robust as possible against QCD uncertainties, but it's not bulletproof. But what you see, and this is a consistent feature, is in this region, the data is high, and it's high by almost 3 sigma in both bins. Okay, so this is excited a lot of attention. So what you can do, you can look at this, and then you can look at the other optimal observables and see if a consistent picture is emerging, and many people think that one is. This is a rather messy plot, but it shows the results from other experiments. So again, we have somehow failed to combine these measurements. Again, I complain about people making a heavy deal of this. No other experiment has the same sensitivity as LHCb, but still, if you stare at this for long enough, what you do see, and indeed the other experiments are using coarser bins for this reason, but in general in this region, if you so black is LHCb, blue is Atlas, red is Bell, green is CMS. So there's this one CMS point which is low here, but everything else is high. So it's looking like the other experiments are supporting this LHCb picture. This does not smell like a statistical fluctuation. And you can look in other decays of the same family, like the charge decay, B plus decay star mu mu with a charge kaon, or BS to phi mu mu. Again, you get behavior which is qualitatively and quantitatively similar. So something is happening. So P5 prime is a very sort of difficult thing to get your head around. Maybe easier is if you think about just looking at differential branching fractions. So this is just looking at the branching fraction, again, as a function of Q squared, the invariant mass of the 2 electrons. And this is for K star mu mu. Where is it? Here. But then all these other decays are decays of the same family. And superimposed are theory predictions, and the theory uncertainties here are large, and the theory uncertainties in these branching fractions are bigger than for these optimized observables. They are less robust, right? But still, what is unmistakable is that in all cases, in this low Q squared region, which is where you had this issue in P5 prime, the data is everywhere low. Okay, so this is adds to the intrigue. So people said, okay, this is good, but what we need to worry about are these theory uncertainties. Can we look at some observable where the theory uncertainties are completely negligible? So this led to the infamous RK and RK star observables. So everything I've shown you essentially has been made with muons. So people said, well, can we do anything with electrons? So at the LHC, doing things with electrons is really rather difficult. So actually making a detailed plot like this with electrons is almost impossible. But what you can do is go into some restricted region of Q squared and there try and measure the respective rates of the decays into muons with respect to electrons. Okay, so this has been done for this decay B to KLL and this decay B to K star LL. And what do you expect in the standard model? Well, it's clear because of lepton universality, you expect unity. Okay, so what was observed? Well, this is something which was lingering around like a bad smell for almost 10 years. So this is unity, but here's a measurement of RK, so that's for the B to KLL thing, and here RK star. So you see in both cases, these are lower than unity. So this is suggesting that the muons are coming in less often, the decays into the muons are happening less frequently than the decays into the electrons. So for a long time, these results generated great interest and many theory papers. However, you should always, this was still not 5 sigma, and there were still things we can do. And, you should always let nature have the last word. Measurements involving electrons at hadron colliders are hard, and when the LHCb data are reanalyzed with a better technique involving both modes and more scrutiny was paid to possible backgrounds, this is what's found. So this plot here is rotated with respect to this plot. So now RK and RK star are on the vertical axis, and measurements have been made in actually 2 bins of Q squared for both RK and RK star. And the message is very, very clear. These results are consistent with unity. So what this tells us is that, some of these mysteries I've shown you, the P5 prime, these low branching fractions, other things such as this, that these are still very much alive. But the idea that there's lepton universality violation happening here, that is dead. Okay. So the anomalies are still there, but this aspect of the anomaly is dead. So there you see it buried, and I thought we'd hear no more about this ever. But only last month, this is, and you can't blame LHCb for this, this is the Bell 2 experiment. This is not a measurement of into charged electrons, but this is a measurement into B to K nu bar. So here you don't know what the neutrino is. It could be any electron whatsoever. But this decay has now been seen for the first time. It's very rare. It's something you can only hope to see at a E plus E minus collider. And the central value seems to be 2.8 sigma above the standard model. And already people are saying, aha, because you're accessing all 3 families of neutrinos here, people like to, already being tempted to attribute this excess not to the electron or muon neutrinos, but to the 3rd generation of neutrinos. And new physics models are being constructed to do that.
So I have a question. The previously anomalous results and the new results which are fully compatible,
Yeah.
What is the internal collaboration consensus on this? Was the previous result just a statistical fluctuation, or did you have something?
No, it was I say this, I was an author, it was a, well, people will say, oh, there's some statistics in here as well, but it was a screw up.
There was some.
There was a background. There was a background of the rate of hadronic hadrons being misidentified. The rate of certain hadronic backgrounds where the hadrons were misidentified as electrons. That was driving this. Okay, there are additional things on top, but
Okay. And in the next plot, you showed this 2.6, sorry, the next one.
Yes.
Yeah. Yeah, 2.8 sigma about the, that. Are these significances local ones or global? Because I assume you're doing similar tests in a large number of channels, right? Or
Yeah, well, this is always a question. This is a local significance.
okay.
With these branching fraction enhancements, when you see this quoted, it will always be local. So yes, you're right. Yeah, you could say, well, what's the, but you know, there's good reason to focus on decays of this sort because they are intrinsically interesting. You wouldn't want to average over every possible B decay. So what we make of this, it's too early to say. This is very, very hot news. Okay. In closing, there's one important message is that you have all these measurements. How can you interpret them? How can you put them together? I just want to flag this up without going into any detail. But you can analyze them in the context of effective field theory. So the theorists in the room will know a lot about this. So this just as Fermi theory is an effective field theory approximation to the electroweak theory, you can do the same thing here. So you can, well, the deal is that you use this operator product expansions. So this is a model independent approach. So you take out the CKN elements, but you then have these operators here, and you can write down all possible operators. And then you have these things called the Wilson coefficients. So you can therefore try and, so whatever rare decay you're looking at, these operators will contribute differently. So they're sensitive to different combinations of Wilson coefficients. So what you can do is you can take all of these flavor changing neutral current processes and try and you attribute, in principle, the Wilson coefficient should be the same in each decay, and you can try and fit those. And the values of those Wilson coefficients are the same in the standard model, but they can be affected by new physics. So I'm not going to dwell on the results of any such fits. This is actually quite a recent one. I'm not dwelling on it because this issue of the reanalysis of the LHCb data is rather fresh. And then also this business from the Bell 2 result is even fresher. So that there's no fits I know of which encompass all of those. But this is just an example fit. So the standard model lies here. So here, all this flavor changing neutral current data have been fitted, and it's favoring a value lying off the standard model. So this is being driven by things such as this P5 prime coefficient, these branching fractions, etc. And then you might ask, well, what do these Wilson coefficients mean? If you have an anomalous Wilson coefficient, what's going on? Well, you can interpret that in terms of new particles, such as leptoquarks or Z primes.
So in this fit, are you assuming all the other Wilson coefficients are zero?
Well, this is one I've just picked out, but yeah, so I don't want to speak to this very particular fit, but generally what happens, yes, you fix a bunch of them to the standard model, and then you float one or two and see what you come up with. Yeah. And then you can try an infinite number of combinations, but what has generally been found is yeah, with the data, certainly you do find anomalous Wilson coefficients however you fit it. For a while, the Wilson coefficients were allowed to be different for electrons and muons. This was provoked by this lepton non-universality scare. I think that will go away. What you see here is a universal Wilson coefficient fit. So I think this is just fitting C9 and C10, putting everything else to the standard model. But you see you're lying many sigma away from the standard model. So then people will come and start saying, well, how clean are these observables? And people will argue about whether the theory uncertainties are really under control or not. So I don't want to speak particularly to any one fit. I just want to flag up that this is how you interpret the data. Right, I want to finish. I have 2 slides and then I finish. So this is so you might think, well, lepton universality, this is now fixed. There's no question that this tenet of the standard model is obeyed. So I've shown you that in BS-LL decays that, I would have told you that's true 2 weeks ago, but then this new Bell result has, the zombie has come back from the grave. But there's somewhere else, there's a completely different class of decay, B to CL new, right? So this is a process like this. This is a tree-level decay. This is not a decay involving a loop diagram. But this decay was originally considered of interest because if you consider the case where the lepton is a tau, then this is a good way to be sensitive to charged Higgs, because Higgs coupled to mass. Okay, so people, already 15 years ago said, well, let's start measuring the branching fraction of these decays where a tau is involved, and we will compare the rate to the case where there's a light lepton involved, where the Higgs enhancement would be very, very small. So in the standard model, if you make, so again, you're making a ratio like this, and you can do it where the case where you've got a D involved or an excited D, a D star. You might just imagine, well, lepton universality in the standard model tells you that the couplings are, the ratio of coupling should be 1, but the tau is a heavy object and there's not much phase space involved. So there's a phase space suppression. So actually the standard model value is less than 1. It's about a quarter for RD star and about 0.3 for RD. Okay, that's where the standard model point is. So that's just coming from a phase space suppression. But it's well known. It's very well predicted in the standard model. There's some lattice QCD goes in there. So people have made measurements, therefore, of this, and they've been doing this for a long time. Here's an early bar measurement, which is very high. So this was already interesting. And pretty much every measurement since then has been high. These measurements are very difficult to make, particularly at the LHC, where there have been measurements coming in. And I'm not going to give you any details about them. All I'm going to say is if you put everything together, you get something like a 3.3 sigma tension. And this tension has remained like that for a decade. So every time someone makes a new measurement, it generally, often the measurement is high, but it might be not as high as before, but the uncertainties come down and you're left with a 3 sigma tension. So this is so this is certainly of interest. The original motivation was from the charged Higgs, but results, and I'm not qualified to explain exactly why, but the results, even though they're high, this is no longer the favored explanation. And people again talk about leptoquarks. You might imagine you could explain this simultaneously with the previous anomalies I've been talking about. People have tried that, but it's a struggle. This is a tree level process. So if you have new physics happening here, if there's a new physics particle there, that has to be relatively light to compete with the standard model contribution. So if there's any new physics happening here, if there's a new particle involved, that new particle could be within reach of the LHC. So here's the same plot again. So my just take-home message before concluding is that this situation is intriguing, and it's been so for like over 10 years. But I think what we really need here is a truly precise single measurement to land a knockout blow. LHC, we've been contributing measurements like this in the last year or so, and that's great. And here's another LHCb measurement we've made, but it would be much. But they don't really clarify the picture. We would like a very precise measurement which would just say this is standard model or this is indeed really, really exciting. So hopefully this will come either from Bell2 or from the LHCb new data. Okay, so let me conclude. So some of the most powerful probes for new physics, which are sensitive to the highest mass scales, are from studies of flavor-changing neutral currents. And many studies are underway, some with an intriguing status. The most powerful and interesting, I think, are the beta mu mu and the beta SLL bar transitions. And I finished by mentioning this tree-level process, beta C tau nu bar, which has puzzled the community for many years. And here we're awaiting a precise single measurement to land a knockout blow. And in all cases, more data and more precise measurements are required. So thank you for your attention. Okay, my chair has left the room, but we can manage maybe. You have a question? Did you have a microphone? Yeah.
Go back to the slide with the Wilson coefficient table, like
Slide with the
slide
Wilson
33,
coefficient.
I think.
This one or going further back? This one?
Yeah, this one. So in this table, what does this cross means? Like for B2L plus L minus, the scalar and C10 prime, they're not like they're not allowed, like constraint in or not contributing.
You're asking why there's no entries here.
Yeah, so cross means no contribution, or
No, that means there is a contribution.
there is a contribution.
Sorry, yeah,
No,
it's ambiguous. Cross means that there's that Wilson coefficient contributes.
I see.
It should be a tick. I didn't make the table.
And is it in the branching ratio or in all of the? For example, in B2 K star L plus L minus, there can be contribution from the scalar operator like CS plus and CP plus.
You're asking what sort of observables are assumed to be involved
Yes.
here. I don't know for this table. I just picked this out because you're right. In some cases, you can just measure the branching fractions. In other cases, you particularly here, you can measure many more observables as well. So I'm sorry, I don't know for this table. This is just indicative, but I think the message is that the different decays, some of them are sensitive to the same coefficients, some have sensitivity to others.
One more question about the optimized observable, the P1, P5. Those are optimized in the sense that the hadronic uncertainties are removed by taking these ratios. Is it true for only for the standard model case, or in the presence of new physics also the observer remain optimized?
Well, the thing you're seeking to minimize is the uncertainty coming from QCD, particularly uncertainty. So I think the assumption is just that new physics we physics. Therefore, on that assumption, then there will be these observables optimized for all cases. If you have new physics turbine form back, then God help us.
Okay, thank you.
Okay. I don't know if really is there anybody on Zoom who might have a question? I guess I should ask that. Just speak up. If you do. Okay, anyone else on the room, or maybe you want to go for the want to chat on the afterwards?
Yeah. So there are some theories they claim that we call it sort of the so-called optimal observable, or like most of the form factor or all like one of our good friend Rahul Sinha and few other they claim these are not as clean as let's say being. But I think from the experimental perspective, like sort of. I mean, what is your kind of sort of?
There are other observables you can pick, and some of the people you mentioned advocate other observables. And well, the data are being analysed in many different ways. There's not a single analysis. So I think the data are being scrutinised from all of these perspectives. So that does not concern me. Yeah, but we're not religiously attached to these observables. Okay, so when we meet again, which I think is on Thursday, we will talk about charm physics and then future prospects. Okay, thank you very much.
Recording stopped.
Yeah.